Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to today's lesson on exponentials and radicals. I am going to start this video which is going over several of the different rules about exponents and how they relate to each other, give you some basic examples that you might remember from junior high, and then we're going to get into some simplifying problems and we will keep going from there. So just a reminder that you'll have a base and a power or an exponent. So again, a is the base, n is the power. So we might say this is a to the 5th power. What that really means is that we're taking a multiplied by a, multiplied by a, multiplied by a, multiplied by a. So this would be considered a monomial because there's no plus signs. And that's what we're really looking at here in the moment, is what happens with exponents on monomials. So the first one we're going to cover is, as far as rules go, is that product rule. And generically, you might see it a to the m multiplied by a to the n. Okay, so a lot of times I find that college students may not be ready to go straight to variables with no numbers. So I tell my junior high kids when I teach junior high that when in doubt, write it out. So let's go ahead and look at that. X to the 5th being multiplied by x to the 3rd. So what's happening here is we have 1, 2, 3, 4, 5 x's, being the first part, being multiplied by 1, 2, 3 x's. So now that I've written it out, we can actually see that this is x to the 8th. So what happens is we took the 5 for this exponent and the 3 for this exponent and we added them together. So that's the rule, is you're going to keep your base, but you're going to add your powers. Now, even if the base is numerical, for example, 4 to the 3rd times 4 to the 5th, that's still 4 times 4 times 4. 1, 2, 3, 4, 5. We still have a power of 8. Our base is 4. It does not become a base of 16 because we don't have 8 16s, we have 8 4s. So make sure you understand that your base stays the same when you're adding those exponents. Okay, so the product rule, if you add the exponents, what do you think that quotient rule might be? Okay, so we would have a to the m divided by a to the n. For example, y to the 9th divided by y to the 2nd. So we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. And we can back it off. We can take 1 away from each, and we can take a 2nd away from each. So we're left with y to the 7th. So this equals a to the m minus n. Which that kind of brings me to my next idea, is let's think about this. What if I had x to the 3rd divided by x to the 5th? Well, if I follow this rule, I'm going to get x to the negative 2nd because 3 minus 5 is negative 2. But if I write it out, 1, 2, 3 over 1, 2, 3, 4, 5. Take away 1 from each, take away 1 from each, take away 1 from each. I have 2 x's left in the denominator and just the lead coefficient of 1 in the numerator. And the thing is these are equal statements. X to the negative 2nd is the same as 1 over x squared. So this is how we fix negative exponents, is we do this. We use basically like a reciprocal. In this case, I like to, instead of actually just subtracting them just straight out, I like to say who has more, the top or the bottom, how many more. However, if you need to fix negative exponents, we now know that we have a negative power rule. x to the negative y is equivalent to 1 over x to the positive y. Also, 1 over a to the negative m is equal to a to the positive m. The negative power causes a reciprocal. Okay, what happens if you have a to the fifth divided by a to the fifth? Well, if we use our quotient rule, we have to subtract our exponents, and that gives us a to the 0. But if we think back to elementary, anything divided by itself is 1. So which is it? Is it a to the 0 or is it 1? It's actually both. And this is why anything to the 0 power will always equal 1. This is your 0 power rule. In case you ever wondered why, you're getting the 0 power by subtracting your exponents, but anything divided by itself is also 1. So anything to the 0 power is like having something divided by itself. And then I find that the next one is the ones that students confuse the most with the product rule. And that's the double power rule. And this is where that when in doubt when in doubt, write it out comes in. Okay, so a double power might be like x to the third to the fourth. So that means we have x to the third once, twice, 3, 4 times. So here, when I write it out, we can clearly see that it's x to the 12th. This is very different than x third times x to the 4th, which is x being multiplied by 1, 2, 3, 4, which is x to the 7th. So we can clearly see when we write it out that these are two different scenarios. So the double power is when you have one base and double powers that are side by side, and that's when you multiply them. Here, that product rule that we did just up earlier is x times x, and that's when we add those powers. So make sure you understand the difference between the two. If you get stuck, there's no shame in going ahead and just writing it out. Okay, so let's go ahead and get into some examples. So our first example is just going to be 2a cubed b squared being multiplied by 3ab to the 4th cubed. And I find that students do amazing at getting the exponents correct on this problem. What I find that students have the biggest error in is that lead coefficient. And the lead coefficient is not going to be 6. Why? Why is it not going to be 6? Well, here's that whole when in doubt, write it out coming in. So we have 2a, b, 3a, 1, 2, 3, 4, 3a, 1, 2, 3, 4, 3a, 1, 2, 3, 4. So now I can clearly see there's a lot of things to multiply. So sometimes I think it helps students to go ahead and focus on okay, let's just look at the number part. We have a 2, we have a 3 cubed. And then we have the a part. So multiplying by, we have a cubed, and we have a cubed. And then we have the b part where we have the b squared, and we have the b to the 4th cubed. So again, I have just written whatever was in here, and I used the power from here and the power from here. Now we know that this power is assumed to be 1. So you don't have to write the power, but that's what I did. I just did that in pink, I did it in purple, and I did it in green. And it does match what we have written out here the long way. Okay, so when we do 2 times 3 cubed, if you grab a calculator, you'll find out that that's 54, because we have to do 2 times 3 cubed. Okay, when we think about it here, this is just a cubed and this is a cubed. So if you picture it, we'll see 6 a's, which indeed 1, 2, 3, 4, 5, 6. And then here we have that double power. So b to the 4th cubed, that's b to the 12th. And then these two b's gives us b to the 14. And if you look at it, that's indeed what we had there. The other way you could have done it is you could have done like order of operations where we do exponents first. So that would be this exponent right here, which would give us 2a cubed b squared being multiplied by 27 because I have to cube the 3, a cubed because I have to cube the a, and b to the 12th because I have to cube the b to the 4th. And then we can do 2 times 27 is 54. We see that we have 6 a's and 14 b's. So any of those ways of approaching it is absolutely fine. We did not solve this because there was not an equal sign in the problem. This was considered an expression. We just simplified an expression. So you solve when there's an equal sign. You simplify whenever you're just making the problem look less complicated. All right, let's try another one. This one's going to have a quotient in it. Okay, so the good news with this one is there's no coefficients, so that normal mistake isn't there. I'm going to go ahead and do that double power first. So because we have powers inside and a power outside, this is considered double powers. So we have x, y. If we have y squared and we write it down 4 times, we'll see that there's 8 y's. 1x written down 4 times, so it would be 4 x's. 1z written down 4 times, we'd have 4 z's. Now if you remember when you multiply fractions, you just go ahead and multiply across the top, multiply across the bottom. Okay, now the numerator is not simplified, but I'm just going to go ahead and kind of think through it out loud. And we're going to be using the product slash quotient. Actually, so who has more x's, the top or the bottom? If you said the top, you're correct because they're all in the top. How many total x's do we see? We see 5. 4 here and 1 here, giving us x to the 5th. Who has more y's, the top or the bottom? The top has 7 more y's because 8 minus 1 is 7. And who has more z's, the top or the bottom? If you said the bottom is the only one that has z's, you'd be correct by saying z to the 4th. Now some of you might have just done subtracting. Yes, this is equivalent to x to the 5th, y to the 7th, z to the negative 4th. However, we generally do not leave answers with negative exponents in their final answer. We generally choose to try to make our exponents positive as much as possible. I know these are equivalent statements, but this one's just in a better, more preferred format. Okay. So let's look at 6st to the negative 4th. And I'm really careful with my t's so they don't look like plus signs. S to the negative 2nd, t to the 2nd. Okay. Focus, come on. So the proper way to do this would it be go ahead and get those negative exponents taken care of first. Okay? Most books are going to tell you to go ahead and do this. 6s to t squared. I'm going to move this from the bottom to the top. And I'm going to move this from the top to the bottom. And that took care of those negative exponents. By the way, what's 6 divided by 2? If you said 3, you're correct. We could write it 3 over 1, but we have other variables going on, so why do it? How many s's do we see total in the top? 3 is correct. And how many t's total would there be in the bottom if we wrote it out? That's right, there would be 6. Now, we could have skipped this middle step and actually gone straight to the answer. So let's look at that problem again from a different standpoint. 6, 2, we've got st to the negative 4, s to the negative 2nd, t to the 2nd. And we could have just went straight to 6 divided by 2 is 3. And that's because 2 goes into 6 3 times. Who has more s's, the top or the bottom? Well, 1 is 3 more than negative 2. So we know s to the third would be on top. And then who has more t's, the top or the bottom? 2 is 6 more than negative 4, so the bottom has 6 more. So it depends on how you want to kind of view that, how you take care of that particular problem. What happens when the negative exponent is not in a numerator or denominator, but instead it's on the outside of a fraction? So you actually have two ways that you can deal with this. You can either deal with a double power and then deal with a negative, or you can deal with a negative and then deal with a double power. And I'm going to look at it both ways. If you want to deal with the negative first, the negative causes a reciprocal. So we could rewrite this as 3z cubed over y to the positive second. And then we would just square each part. 3 squared is 9. Z cubed squared is z to the 6th. And y to the second power is y squared. So that, again, is taking care of the negative power first and then the double power second. The second way that we can approach this is by doing our double powers first. So if we do that, that would become y to the negative second, 3 to the negative second, z to the negative 6th. And then after that, we're going to have to fix our negative exponents. Everything that's negative in the denominator will move to the numerator. Everything that's negative in the numerator, we're going to move to the denominator. So 3 to the negative second is going to go up to the top and become 3 to the positive second. Z to the negative 6th is going to go up to the numerator, become z to the positive 6th. And y to the negative second is negative in the numerator, so it will go to the denominator and become y to the second. Hence, getting to that same result of 9z to the 6th y squared on the denominator. So there is that case as well. Now, you might have said, well, I've not really worked with negative exponents before. I have a feeling that you have. You just may have done it more in the science classroom, because we have worked with scientific notation, and that goes right in hand with what we're doing about here. So scientific notation is just a way of writing numbers so that we don't have to write all the zeros. And it's just kind of a mathematical shorthand. So think about it this way. 3 times 10 to the third. That would be 3 multiplied by 1,000, which is 3,000. So a lot of people think of it as 3.0, and because 3 is positive, we move the decimal in a positive direction or to the right 3 spaces. And that's how we can get the 3,000. So let's say I give you information that like A is 0.123442. B is, and C is 2 times 10 to the negative 18th. Now, I'm definitely not going to type this in to my calculator with all the decimals, because that would be a lot of zeros. So if I want to, let's say, evaluate, I don't say solve because, again, no equal sign, evaluate A, B, C. It actually is a lot nicer if I move these into scientific notation so that I don't make errors in the calculator. So 4.2, see how it's a decimal? It's like they have divided by tens. Instead of multiplying by tens, they've divided by tens. 1, 2, 3, 4, 5. So that's why we write it as 4.2 times 10 to the negative 5th. Because they were dividing by 10 5 times. Every time you divide by 10, you move the 0, right? B is really 3.1 times 10, and 1, 2, 3, 4, 5, 6. So times 10 to the 6th. So again, I'm counting decimal places. You always have one number, non-zero, in front of the decimal, and then everything else is after the decimal. And then dividing by C, that would be dividing by 2 times 10 to the negative 18th. And there is technically unassumed parentheses going on here. And especially if you're writing this into a scientific calculator that doesn't have the ability to do vertical fractions, you would need the parenthesis. And I will have you look at that in 2 ways when I do get the calculator out here in a second. We can reorganize this. We can like change up the order of multiplying and dividing, because remember, dividing is technically multiplying. So I'm just going to commute the orders here a little bit, and I'm going to go 4.2 times 3.1 times 10 to the negative 5th times 10 to the 6th divided by 2 times 10 to the negative 18th. And so I wrote it without the multiply symbol. I used parentheses instead. Now, if you just do this in a calculator, you will get 6.51. And that's pretty simple to type in a calculator. Then, who has more tens, the top or the bottom? So the top has a total of 1 10. The bottom is 10 to the negative 18th. I think you would agree 1 is 19 more than 10 to the 18th. So we'd have times 10 to the 19th. Or if you think about it, I'm going to rewrite just this part over here. Move the 18 up and the 5 down. I fix my negative exponents, right? 18 and 6 makes 24. 24 is 19 bigger than 5, so that if that helps you see the tens. Okay, so this is our actual answer, and it's in scientific notation. It's a very big number because multiplying by 10 to the 19th has a lot of zeros, and multiplication makes your answer bigger while division makes your answer smaller. So let's look at this original problem, and we'll also look at some common errors with it. So in this calculator, I use my alpha button and my white one, and it brings up this fraction menu. Some of the calculators you can use the green button and then the button right next to it, and it will do the same thing. I don't remember if this calculator does. Let me turn the brightness down a little bit. This one happens to. So all I did was green X, and it brought up a fraction. The reason why I like the Y1 better is if I do that, I get a menu of numerator, denominator, mixed number. I can also change it from an improper to a mixed, or from a mixed to an improper, and I can also change it from fraction to decimal. I just have to choose menu 1, 2, 3, or 4. And to do that, I just type 1, 2, 3, 4, whatever number's next to it. Okay, so for our numerator, we have 4.2 times 10 to the negative 5th. And you have to arrow over to get back to normal size. And we have 3.1 times 10 to the power of 6. Then arrow to the denominator and do 2 times 10 to the negative 18th. And again, I forgot to arrow over. And this E thing really means times 10. Not sure what's happening with my lighting here. Okay, so this 6.51 times 10 to the 19th is the same thing that we got. They just use an E. And could you use E when you're typing it in as well? You could, but you have to make sure that you know which E button to use, because lowercase e does not work the same. So I generally just prefer times 10. There is a button if you don't like doing 10 exponent. There is a button right here, and on this calculator it's blue, so you'd have to touch the blue button to get this to pull up. It will do the same thing. It'll type 10 and let you just type in the power. I prefer to just use the caret key and type it in manually. Okay, so I did want to go over some common mistakes. So let's say you don't have this kind of calculator, and you just do 4.2 times 10 to the negative 5th times 3.1 times 10 to the negative 6th. Whoops, not negative 6, positive 6. Divided by 2 times 10 to the negative 18th. that's not the same answer. Why not? Well, by not putting parentheses around this, it did a different problem. It did all that work divided by 2, and then it took that answer and multiplied it by 10 to the negative 18th. If we wanted to do this horizontally, we would need to have parentheses around the entire numerator and parentheses around the entire denominator. Now we're getting the same thing. So that first time I typed it into the calculator horizontally, instead of typing this problem in, the calculator heard me or thought I said this. Okay, so these are two very different problems, which is why the calculator was giving us two very different answers. So that's why parentheses around your denominator are very important, especially if you have more than one thing in your denominator. So if you're ever in questioning, just put parentheses around your entire numerator and your entire denominator, and that will save you a lot of order of operations error. So we must make sure that we know how to communicate with our exponents, and we also need to make sure how we communicate with our calculators. Okay, now all these exponent rules actually apply to our radicals, but the reason is because of the relationships between radicals and exponents. So we can actually change from radical form to exponent form and back. So the fourth root of a cubed. Okay, well, that's actually the same as a to the 3/4. So you'll notice that my exponent is a fraction. That's correct because the fourth root actually undoes the fourth power, technically. And so there is this relationship between, how close are we to being able to, well, I need a group of 4 to make this work out evenly because it only works perfectly if a is to the 4th, and I'm not there, I'm only at 3/4 of a group, hence the 3/4. So b to the 2/3 would be the same as the third root of b squared. How many of you know what 4 to the 1/2 power is equal to? Well, the 1/2 power, 4, 1, 2. But the power of 1 is understood and the index of 2 is understood. So it's really the square root of 4, which happens to be 2. So keep in mind that the 1/2 power and the square root are the same thing. Rewriting them in different forms can actually make math easier for you at different times. Okay, so keep in mind the fourth root of x to the 4th is equal to x to the 4/4, which reduces to x to the 1st. Or fourth root, fourth power, they cancel each other out. The only thing is anytime you have an even index, if you ever get rid of the radical sign when you have an even index, you need absolute value signs on here so that you can keep it in the real number system. You only need the absolute value on variables. Not on numbers. When you have an even number on your index and an odd power in your answer. Why not with an even power? Well, x squared is always positive, so the absolute value is redundant. X to the 3rd is not always positive, so that's why. So it's that even odd relationship, even index, odd power. So why would I be talking about that? Well, let's look at the fourth root of x to the 7th. Okay. The proper way to do that would be to change this into the fourth root of x to the fourth multiplied by the fourth root of x to the third, because 4 plus 3 is 7, right? We split it up using our powers. This, that's even, so we're going to need our absolute value. And that would be our final answer, because it's reduced because the number inside is smaller than the number outside. Okay, you could have thought it as this. The fourth root of x to the seventh is equal to x to the 7 over 4. 7/4 is 1 3/4, which is why we have 1 3/4. Odd power, even index, keep it real. That, however, is not how I like to teach my Algebra 2 students. I have some videos on how to reduce radicals in my Algebra 2 videos. I like to go 1, 2, 3, 4, 5, 6, 7. And I like to think about grouping. So like folding socks, okay? You put all your socks in a basket, you fold your socks. The dryer somehow manages to eat some, so you have leftover socks in perfect pairs. This tells you how many legs the person you're folding, or the animal you're folding socks has. So in this case, we have a four-legged friend that has socks in sets of 4. Maybe it's Fido, right? You want to put some little booties on him before you take him outside on the hot pavement to protect his feet. Okay, so we've got to fold them in groups of 4. So we have one group of 4. And somehow there's 3 left in the basket because maybe the dryer ate one of them. I don't know. The dryer likes to take all those socks, right? And of course that even-odd relationship. So that's 3 ways to look at the same problem. 2 of them are a little more book method, and one of them is just kind of a thinking about it method. So you can use the split it into 2 different radicals. You can use the improper fraction to mixed number fraction, or you can do folding socks. And again, it's reduced when the number inside is smaller than the number outside. So I'm going to go ahead and utilize more of a book method than a folding socks method. If you want the folding socks method, you can always go back and watch some of my previous videos. But we're going to elevate our thinking level. So I'm going to rewrite these in prime factorization. We know that 50 is 2 times 25, and 25 is 5 times 5. So this is the square root of 2 times 5 squared. 200 is 100 multiplied by 2, which is 10 times 10, which is 5 times 2, which is 5 times 2. So that would be 2 cubed plus 5 squared, or no, plus multiplied. Okay, so now that we have a prime factorization, I'm going to rewrite this using some information about my square roots. I have the square root of 2 being multiplied by the square root of 5 squared. And I'm only going to use a maximum of a 2 for a power. So here I have 3 2's. So I'm going to do 2 2's times 1 2. So you'll notice that my exponent inside never went higher than my index. Remember that index is that assumed number out here. Okay, anytime we see the index and the power match, it reduces. So here on this 5, the index and the power match, so they cancel each other out, and we're left with 5 being multiplied by the square root of 2. The index and the power match, so there's a 2. The index and the power match, there's a 5. And of course our square root of 2 comes down. So order of operations says I can go ahead and multiply these. Now, I can add like terms, and you might go, well, how are they like terms? Things like that. If I had 5x plus 10x, wouldn't I make that 15x? And the reason I can do that is because the x is a GCF, so I'm going to factor it out to the end. And we see there clearly the 5 plus 10. So I'm going to factor the square root of 2 out to the end here. and that gives me 15 square root of 2. So they work exactly the same, and we were able to combine like terms. You might be able to think about it and go directly from this step down to this step without having to do that factor stage. But you must reduce your radicals anytime you're working with them to the smallest number possible. So we always want, if we can, a prime number underneath our radical. It is not always possible, but we try for it. So let's see if you can evaluate the next one without using a calculator. Okay. 8 to the 2/3 power. And I know your scientific calculators can handle this, even your basic ones, your phone calculator can handle it, I promise. But there's a couple ways we can think about this. We can think about this as 8 squared to the 1/3 power, because 2 times 1/3 is 2/3. Or we can think about this as 8 to the 1/3 power squared. Or we can think about it as 2 cubed to the 2/3 power. So here I split up the exponents by putting the whole number inside and the rational number outside. Here I did the opposite. And here I changed the base from 8 to 2 cubed. Okay? So if you decided to do the first one, we would have 64 to the 1/3 power, which is the third root of 64 to the first, which is 4, because 4 times 4 times 4 is 64. Now that we've refreshed your memory that the 1/3 power is the same thing as the third root, we could do the third root of 8 squared. The third root of 8 is 2. 2 squared is 4. Or now we have double powers, so we multiply. 3 times 2/3 is 2, and 2 squared is 4. All three methods are proper and correct. It's just a way of which way does your brain go? Can you go ahead and switch to this way and use your exponent rules? Or do you need to think of it as the third root of 8 squared? You either do the third root of 8 first and then square it, or square it first and then do the third root. That's up to you. Now, due to history, just a quick history lesson. The square root of 2 is 1.4142. Okay? Would you rather do 1 divided by the square root of 2 by hand? Meaning you would have to do long division, put up a 0 and things like that, because look at this answer, 0.070, right? 0.707106, on and on and on. Or would you rather do the square root of 2 divided by 2? Now think about that. Here's the square root of 2, and if I divide by 2, I get, well, what's half of 1.4? 0.7, right? I get the same answer. So prior to calculators being a thing, anytime they had a radical in a problem, they would have to go to a chart where somebody had created this chart using advanced math. And they would go, oh, the square root of 2, and in the chart they would find this decimal. Well, they didn't like doing this kind of division. They wanted to do this division. So why is 1 divided by the square root of 2 the same as the square root of 2 divided by 2? Why are these equal? Well, what happened is they said, okay, look, I know that the square root of 2 squared is just 2 because these cancel out. But with fractions like 1/3, if I square 1 and I square 3, I get 1 over 9. Those are not equivalent things. That's not going to help me. So I can't just square top and bottom. However, if I do 1/3 and I take it times 3, I get 3/9. Now 1/3 does equal 3/9. So they can't square top and bottom, but they can multiply it by itself. And whatever you do to the bottom, you do to the top. 1 multiplied by the square root of 2 is the square root of 2. And the square root of 2 multiplied by the square root of 2 is the square root of 2 squared, cancels out, we just get 2. So that's why they're the same thing. It's just like we got common denominators by multiplying the numerator and denominator by the same thing. That's what they're doing. So it's called rationalizing the denominator. Okay, it means we're taking the denominator from an irrational number and creating a rational number. Now, normally when that happens, the numerator becomes irrational. We are okay with a long decimal in the numerator because a long decimal divided by like 5 is better than 5 divided by a long decimal. It's this here that we want to be a simple rational number so that we could do division without the calculators back in the historic days when the Greeks were creating all this math that you guys love so much. In my classroom, I have a poster of mathematicians from like BC and everything else, and sometimes I refer to it as, hey, when the old dead guys came up with this stuff, because obviously they're no longer living with us, but they're the reasons why we have the rules that we do today. They did not have technology. Why do you have to know this? Well, you might write a computer program or something, who knows? Plus, it's what's in the math class. So here, 1 divided by the 3rd root of 5. I have to multiply by something, and I'm going to write it in 2 ways. I have to multiply by something to make this a perfect group. So I need, in the denominator, I either need, if I'm writing it in radical form, the cube root of 5 cubed, or 5 to the 3/3. I need one of those two things to happen because 3/3 is a whole. So what am I going to have to multiply to get to that? So if I just multiply by the cube root of 5, numerator and denominator, do I get 5 cubed underneath? No, there's only 2 5s. I need the cube root of 5 squared. So that in the numerator, I have the cube root of 5 squared, and then the denominator, I have the 3rd root of 5 cubed. Or the 3rd root of 25 over 5. Or over here on the right, I only have 1/3 of a group. I would need to add 2/3 to get to a whole, because 1/3 plus 2/3 is a whole. So now that would give me 5 to the 2/3 in the numerator and 5 to the 1st in the denominator. Why do I not just subtract it and say 5 to the negative 1/3? Because now I have a negative exponent, and to fix a negative exponent, you put it in the denominator. Wait, now I'm right back to where I got, right? So we don't want to go there because we don't want negative exponents. Okay, so let's try that with a variable. The 7th root of b over a cubed. Okay, so b in the numerator is not a problem. I'm going to rewrite it like this. Okay, I need to multiply to get to a whole group. Right now I only have 3/7 of a group, so how many more would I need? I would need 4/7, because 3/7 plus 4/7 is a whole. Whatever I do to the bottom, I do to the top. So this would give me a to the 4/7, b to the 1/7, all over a to the 1, which I don't have to write, or the 7th root, a to the 4th b over a. The other thing I can think of is multiply bottom by a to the 4th and top by a to the 4th. Now, Why could I do it like this is everything is underneath a radical still. So that's why I was able to do that. I'm keeping them equal, and the 7th root is over all encompassing. So this now gives me the 7th root of a to the 4th b over a to the 7th. Now I'll split it up, and I'll have the 7th root of a to the 4th b over the 7th root of a to the 7th, which then that reduces. Why do I not need absolute values on this denominator? Well, because that number is odd. The index is odd, so I don't have to worry about keeping it real. And again, it only works on variables. Now, I will point out that these were monomial denominators. If you ever have a plus sign or a minus sign in your denominator, it does work differently, so you do need to be careful with that. In upcoming videos, I will discuss the difference between a monomial versus a binomial versus a trinomial, but remember, mono means one. So these problems, again, did not have a plus or a minus in the denominator or the numerator. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.